Yeah, so actually we have a very long long history of association. So actually we first met, it must be something like 15 years ago. Right? 20 years ago. And then Thiêm, after his master thesis, went over to Taiwan to with me for 1 year. And during that time he met Alex Lazarian. Right? At that time working at Wisconsin, he's still at Wisconsin. He's still at Wisconsin. So then after 1 year, so Thiêm went to Wisconsin to work with Alex. And after I think 5 years, he got PhD. 6 years, he got his PhD, and after that he has a long history of very active research. Very active research. So I hope that in the near future we can develop more close collaboration between our research group and also between IOP and QUÄC. And hope that in April we meet you in Taiwan. Okay, so let's start.
Okay, so thank you very much, Chu. It's a very nice introduction. It's my great pleasure to be here. Actually, this is my first time doing the talk at the Institute of Physics. So I'm very excited. So yeah, I would like to first thank Đình who has enabled me to learn and do research in astrophysics. So without him, I couldn't enter for research in astrophysics. So he was my master thesis supervisor. And during that time when we worked on the thesis, most of the time we worked through the distant, remote distance. At the time there were no COVID, but we must work from distance because he was in Taiwan and I was still in Vietnam. So we met just 2 times before my thesis.
Very efficient.
Yeah. So yeah, I think it's also thanks to Chung who introduced me to Alex Lazarian so that I could do a PhD with Alex. And from Alex I learned about physics and magnetism. So today I'm going to talk about how the interplay between gravity and magnetic fields actually shape the cosmic ecosystem. So as you know, when we talked about ecosystem, we talked about life and the environment surrounding Earth. But for cosmic ecosystem, actually, it's a little bit different. So in cosmic ecosystem, there may be life, but it's still uncertain. But most of important objects in cosmic ecosystem include gas, dust, stars, planets, and now we know that there is a black hole in the cosmic ecosystem. So in our cosmic ecosystem, we have objects, including black holes, gas, dust, stars, planets, life, and all the environment surrounding those objects. But the question now regarding about the evolution of the cosmic ecosystem, like how gas and dust turn into stars and planets and also life. And also how the black hole in the center of galaxies grow by accreting matter from the surrounding environments. And then the whole galaxy now interacting with the circumgalactic environment. And there is an interaction between objects and the environments in the broader sense. But when we think about the physics, because I was a physicist by training, so I would like to understand from the most fundamental, actually, like how the fundamental forces actually regulate the evolution of the cosmic ecosystem. So we know that there are 4 fundamental forces: like weak force, strong force, gravity, and electromagnetic force. But for astrophysics, so most of the time we care about gravity and magnetism, because they are 2 most universal forces in nature. So we are trying to understand how these 2 fundamental forces interplay with each other and regulate the cosmic ecosystem evolution. So in order to solve this very big question, we have a number of very young and very well-motivated researchers. Most of them are actually young researchers from Vietnam, so I'm very happy to work with them. And one postdoc from India that I'm working with here. So she's now working on understanding the gravity and magnetic fields surrounding the black hole. And for other researchers, for example, with Diep and now here, we are trying to understand how gravity and magnetic fields affect the formation of young stars. And with my students, we are working on understanding how the dense molecular clouds collapse to form young protostars and also planets. And with the other student, we are working on understanding how very old stars evolve and then die, and also feed back into the same planet. So this is a coherent picture, and it shows you that it has a very important in understanding the whole cosmic ecosystem by looking at the post-fundamental forces, gravity, and magnetism.
You also look on the life as well.
Oh yeah, the life.
Biological.
Yeah, that is also something. Because in the ecosystem, we must talk about life, so that's why I have it. Okay, so first of all, I talked about the ecosystem, including gas and dust. And in fact, the mass of dust is just 1% of the total gas mass. But it is a dust that makes the universe very, very beautiful. Without dust, you see that the universe is quite boring. Here you can see in the night, at night you can see in the Milky Way we have a very dark and bright. So for bright doors actually stars, and dark actually dusty clouds. But it is in optical. But though dust particles are actually emitting in longer wavelengths, like emitting flare. So here is a beautiful star-forming region seen by the $10 million telescope, JWST. And here's a whole galaxy seen at fine flare, like about 800 micron or so. And with the dust can also allow us to see in very small scale regions, like the size of our solar system, like 100 AU. So here is a beautiful image of the very popular HL Tau seen by Alma. So this dust makes the universe very beautiful. Yeah, so how about magnetic fields? Actually, the universe is also magnetic. And the first observation that discovered the magnetic fields between stars was by Hall and Hewler in 1949. It's more than 70 years ago. So at the time, two American researchers, they observed the starlight, the life of distant stars. So usually the life of stars is unpolarized. That means the electric field of the light is isotropic. But the two researchers independently discovered that the life of distant star is polarized somehow. The polarized, I mean, the electric field of the light tends to oscillating around only one direction. So they quickly recognized that the environment, or the medium between stars, is not vacuum. It must contain some solid particles. Because if the interstellar medium only contains gas, and then gas should not polarize starlight. And because it's starlight in optical, so the size of solid particles should be comparable to the wavelength in optical, I mean less than 0.5 micron. Okay, so in order to polarize starlight, so the solid particles must be not spherical, because if solid particles are spherical, they just do not induce any polarization. So the conclusion here is, okay, so the solid particles, so we call it dust particles, must be elongated. So elongated like. So if the dust particles are elongated, but if they are randomly oriented, so there's no preferred in the orientation. And then overall, along the line of sight, so the net effect would be not polarized. So the conclusion here is, okay, dust grains elongated, but they must be systematically aligned. And the direction along which that dust grain align with is a magnetic field. So this is a kind of inference about the interstellar magnetic fields from dust extinction. So to understand why the alignment of elongated grains can polarize starlight, we can see it here, a simple picture. So we have a background star here. And here is the environment with dust grains which are elongated and aligned with magnetic field. So the alignment with the long axis of the magnetic field. So those dust grains will absorb starlight. But the absorption is not isotropic. The absorption is stronger along the long axis and weaker along the short axis. So the light which is transmitting through the cloud will be polarized because the electric field that now is oscillating along the short axis. So the starlight becomes polarized with the polarization vector along the magnetic field. So if we observe the polarization, and then we can infer the magnetic field. So that is the implication of polarization. Okay, so the same dust grains, when they absorb starlight, and dust grains are warmed up, so like a black body. So when they warm up, they will emit thermal radiation in long wavelength. And the thermal radiation is also polarized because of grain alignment. So here is an example. Because in the case of emission, the grain tend to emit stronger with electric field along the long axis. And electric field along the short axis is weaker. So the thermal emission now has electric field along the long axis, so which is perpendicular to magnetic field. So by observing the polarization of thermal emission, we rotate by 90 degrees, and then we get the magnetic field. And this is exactly what Planck satellite is. So here's a full sky map of galactic magnetic fields obtained by Planck satellite. So you see it's very beautiful, and the magnetic fields overall along the galactic line here is quite parallel to the galactic line. But the magnetic fields change direction. And you see that the picture is quite not so coherent. It has a small scale fluctuation. And those small scale fluctuations tell us about how magnetic fields turbulence is. And the turbulence of magnetic fields and also fluid is another very fundamental and difficult problem, which even Heisenberg couldn't solve it. So I will not talk about turbulence because it's too difficult for me.
So, Tim, what's the size of dust particle in
the size of dust
you're talking about?
Yeah, well, here for this picture, the size is less than 1 micron. Yeah, but the size could go up to 100 microns. So if we go to small scale of the disk, where planets are forming. So we start with small sizes. Okay, so now we have not only dust polarization as a tool to observe magnetic fields, but astronomers can observe magnetic fields using different methods. For example, using the Zeeman effect. You already know that, I'm sure. But the Zeeman effect is applicable for atoms or molecules that have unpaired electrons. And we only can measure the magnetic field along the line of sight. We can also use the synchrotron polarization to measure the magnetic fields. Because the synchrotron actually is produced by the emission from relativistic particles which are spiraling around magnetic fields. So it has a limited application actually for the very diffuse medium. And using finite rotation, we can also measure the magnetic field. But the most popular technique to measure magnetic fields is using dust polarization, because dust is the most ubiquitous in the cell. Other effects using dry killer fields or ground state atomic alignment, we can also measure magnetic fields. But I will not talk about that. I'll talk about transportation. And I just realized that TRUNG has been also working on the polarization from laser lines. And this is a very promising technique, especially for measuring magnetic fields in the planet forming disk. Because in the disk, so far, mass polarization may not be traced in magnetic fields. So we have to look for other techniques. Okay, so yeah, so far we have so many telescopes that have a polarimetric capability. So using those telescopes, which cover different scales, from very large scale to very small scales, we can obtain the magnetic fields over the whole universe. Okay, so here I show you some example about the different magnetic fields observed in different scales. So here is the magnetic fields observed by JCMT. It's a long filament. So the filament here has a scale, physical scales about tens of parsecs. And here is the smallest scale. This is the region where a young star is forming. So young stars are forming here, and here's the magnetic fields. And ALMA can tell us about the position and hopefully magnetic fields on the AU scale. So here's and we now also discover magnetic fields in very, very early universe. For example, recently the observation by Gish et al. Published in Nature, they use an ALMA, and then they can measure the magnetic fields here at the redshift of about 2.6. And I heard that their latest paper, they can measure magnetic fields when the universe is just 100 million years old. So it's very early. So magnetic fields, you see, they look very beautiful. But for physics, we care about their impact on the gas and gas motion and formation of astrophysical objects. So we start here with the simulation to see how magnetic fields affect the gas motion. So by solving the magnetohydrodynamic equation, they can follow the evolution of a gas cloud. So here are the two snapshots from simulation. For the first day, the magnetic fields are very weak. And for the second day, the magnetic fields are strong. So you see that in the weak magnetic fields case, the turbulence tend to randomize the magnetic fields. And then you don't see very clear organized structure, because all those structures are caused by the turbulence. So fluid turbulence tend to randomize the structure. But when the magnetic fields are stronger, so you know that magnetic fields induce some magnetic pressure. So usually the matter tend to flow along the magnetic field lines. And matter cannot cross the magnetic field lines. So one thing here is matter here is ionized. So it's kind of like a plasma. So plasma cannot cross the magnetic field, but plasma can flow along magnetic fields. So you see that if magnetic field is strong, so magnetic fields can only allow matter to flow along the magnetic field. So you see the structure here is very strong. So this is a theoretical prediction, and this is from simulation. In order to test the picture, we have to observe, and that is the next goal of our study. Now, about the another effect of magnetic fields. So from observation, we know that stars usually form inside the filament structure. But the question, how is the filament to be structure formed? And one of the model for the formation of filament here is, okay, so the filament formed by the conversion of atomic gas. So each supernova can expel a bubble. And then here's one bubble. So when two bubbles, they collide with each other. They compress atomic gas and form the regular gas here. Okay. And so basically in the compression region here, we have a shock. But the shock here is magnetized. So if the magnetic fields in this case, and the shock is coming along this direction, so the shock now act to bend the magnetic field. So the magnetic field are bent in the shock. So matter now can flow along the magnetic field lines, along the direction. So it will produce the cylinder structure. And in this cylinder structure, magnetic field is perpendicular to the filament, as you can see here. And one of the predictions for this filamentary model is magnetic fields should be perpendicular to the filamentary structure. And people are trying to test this model, and our own collaboration also mark the magnetic fields in this called snake filaments. And this filament you see in here, the magnetic fields tend to be perpendicular to the filamentary structure. So this is supporting the theory for electromagnetic field of field formation.
I'm sorry, can you go back to?
Okay, okay.
So, so you said the shock bends the magnetic field,
Yeah.
or the magnetic field bends the shock?
No, the shock bend the magnetic field.
How?
Because the shock is like we have a gas flow moving with high speed. So it's the kinetic energy of gas flow bend the ambient magnetic fields. Okay. So the magnetic fields are not so strong enough to push on the but here we have the shock is coming in the direction.
Bên năng lượng.
Yeah. So the shock actually is just a gas flow moving with high speed. So the kinetic energy is quite large. And the magnetic energy here is not so strong enough to fight back. Okay, now let's move on to the smaller scales. We call it the very dense core. So in the dense core here, so actually the magnetic fields are rising, and gravity actually tends to pull matter to the center and forming the protostar here. But because the magnetic fields, matter cannot cross the magnetic field lines, but matter tend to be easy to follow the magnetic field lines. So we first form the flattened structure, and we call it like a disk. But because the cloud is also rotating, so when it's collapsing, the core is rotating faster and faster, and then while the magnetic fields are trapped into the disk here, and in the disk structure, and the magnetic fields have like an hourglass shape, and the disk is forming here. So the disk here, in the disk here, the matter can be transported outward, and then it reduces the angular momentum of the disk, and then it facilitates the further accretion of protostar, and protostar can be formed. And here is a beautiful picture from James Webb Space Telescope that show very beautiful outflows of the protostar. And here the disk is quite small here, the outflow here. And magnetic fields in this picture, it have to transport matter from the disk to the outflow. And this is quite important thing. But it has not been tested actually, so we need to test it. And now how about the planet formation? And we know that the planets like Earth form from dust particles. But if we follow the process in which stars form, and planets and stars are actually forming at the same time. So initially, for example, the molecular cloud here, and then we go to smaller scale, the cores, this, and then the this here. And here's a range of grain size that we are working with. So in the early stage, like in the diffuse medium, the grain size is quite small, less than 0.1 micron. But when we go to denser and denser region, grain size increase, and it can go up to 100 micron and go to pebble size. The pebble size you can see on the picture. And then pebble size continue to grow, and then eventually to form planets. So this is very complicated. Yeah, so the magnetic fields are also important for the process in which grain growth and planet formation. So here's our own model. For example, if the dust grains are aligned, and then they are drifting across a magnetic field. So here dust grains can cross magnetic field by another mechanism, not by charge particles. Actually, because dust grains are accelerated by a gyro-resonant effect. So if dust grains are crossing magnetic field, and then at the same time they align, so the flip effect, for example, if two initial grains, they are aligned and then they collide, so they form a binary structure. And after some time, this binary structure becomes aligned with magnetic field. And then it continues to collide with another grains. And then it becomes aligned with magnetic field. And eventually, the continuous collision will form a dust aggregate consisting of a binary structure. You can see here. And the dust aggregates are those particles which are found in comet or in asteroid. For example, the European Space Agency has a mission named Rosetta. So in Rosetta, they can collect some dust sample from comet Rosetta, and then they, based on the dust sample from comet, they can use a microscope to look into the dust structure. And then here the dust interstructure, which is actually elongated shape, and inside is made of iron cluster. So this binary structure is consistent with our theory, and in our picture, grain alignment depends on iron cluster. So the presence of iron cluster helps dust grain to be very efficiently aligned. I will talk about that later. Now, another effect of magnetic fields. So usually we think that magnetic fields have a northerly effect on the life, but it's quite surprising. So before talking about the effect of magnetic fields on the life, we talked about one of the key biosignature for the life on Earth, which was discovered by Louis Pasteur in 1848. So at the time, Louis Pasteur found that biological molecules somehow have a homochirality. So to understand what is chiral structure, we think about the left hand and right hand. And for biological molecules like amino acid or protein, they have a chiral features. And for example, this is a amino acid, left hand and right hand. But though molecules are chiral, because when you superimpose to left hand and right hand, this is not the same. So basically, you cannot superimpose left hand and right hand. So these are chiral molecules. But the question now, in biological molecules, we always have a left-handed amino acid. We don't have a right-handed amino acid. So for sugar molecules, sugar have only right-handed molecules. So why nature provide the life on Earth as such asymmetry, and which is the reason for asymmetry breaking? And here we propose one mechanism, which is like basically chiral symmetry breaking can be caused by electrons, which are also chiral. So we know that electrons have a left-handed and right-handed spins, like up and down spin. But when the polarized, we call it polarized electrons, when polarized electrons interact with chiral molecules, so due to some effect named the chiral-induced spin selective effect, which is described by Hamiltonian. So maybe for physicists, you are familiar with Hamiltonian. So the cis effect tells us about the interaction between the electron spin and the chirality molecule. So the polarized electrons can cause the chiral symmetry breaking. And here we suggest that if dust grains are aligned, that means all electrons in dust grains are lined up. Now, the photoelectric effect can release the electrons. So the electrons released from aligned dust grains actually have only spin up or spin down. And though photoelectrons will interact with chiral molecules, And then due to the seize effect, for example, here in this case, the right-handed photoelectrons will prefer to interact with left-handed molecules. So after that, we produce asymmetry in chirality. And even though for initial small asymmetry, but due to some amplification mechanism, it can enhance the asymmetry. So that is one possible mechanism to cause the symmetry breaking in the astronomy.
What kind of interaction we are talking about? This one? That's
So
the plus
here-
sign.
Yeah, so for example, this is quite a deep equation. So the kind of molecules actually here, here's the chiral axis, and here as a spin, electron spin, here is the momentum of electron. So the chiral molecules have some magnetic field, and then the magnetic field can interact with the electron magnetic moment.
Yeah, I understand. But then how the electron go into this the molecule?
Okay. So for example, this is through collision. Through collision.
So they mean it's kind of replacement.
It's just going through the molecule. It may be absorption or it's just going through the molecule. So I can show you more slide here.
Okay.
Maybe I have a backup slide. It may be too technical, so I don't. Yeah, so here's the chiral structure. And so, for example, here's the chiral molecules, and this is the chiral axis. So when electron here is going through the molecule, it will interact with the electric field from the molecule, and then interaction.
That leads to the destruction of the.
Oh, destruction, yeah, that may cause a destruction, but here the electron have only low energy, because a few EV only. And yeah, the destruction issue is actually the problem that disfavor the electron from beta decay. So in the electron in beta decay have left-handed spins. So soon after the discovery of the parity violation, people explained that maybe the chirality in molecules is caused by high energy electrons. But high energy electron from beta decay can destroy molecules. But here photoelectrons have a low energy, so they do not destroy molecules. They can enhance the chirality. Okay, so we already discussed several important effects of magnetic fields. Now, in terms of research, how we can test the theory? Because theories, yeah, we can develop our theories, but for science, we must test theory. So it goes into okay, how to measure magnetic fields in order to test their importance. So, as I already mentioned, the popular technique to measure magnetic fields is using dust polarization. So basically, by observing the dust polarization, we got a map of polarization vectors like this. So the map here is the polarization vectors projected onto the sky. Yeah, from this map, we need to measure magnetic field. And from 1951, China Fermi and also Davis, they proposed a technique to measure magnetic fields using the dust polarization. And actually, Fermi was motivated by the discovery of interstellar magnetic fields, and then at the time he proposed a mechanism to explain the acceleration of cosmic rays. So you know, cosmic rays were discovered in 1930 something, but why cosmic rays can move such fast? And Fermi proposed that maybe interstellar magnetic fields act to accelerate cosmic rays. So that's why he was interested in measuring magnetic fields to test his theory. So the idea of the DCF method is simple. So if the magnetic field is just regular, it's just a straight line. But usually magnetic field is quite turbulent. And in the simplified picture, we can decompose the turbulent magnetic field into the regular component and one turbulent component. Okay. And here the turbulent component is perpendicular to the regular component. And then when we have turbulence, the magnetic turbulence induces the Alfvén wave. So the Alfvén wave is vibrating in the ISM, and with the assumption that if the turbulence energy is comparable to the magnetic energy, and then the fluid turbulence here has a velocity dispersion delta V, so the turbulence kinetic energy is delta E. And the turbulent magnetic energy, delta E, is proportional to the delta V squared. And then if the turbulent kinetic energy in equilibrium with magnetic energy, and then we can get the relationship between the turbulent velocity and Alfvén speed. And after some algebra, we get the magnetic field strength in the planetary sky, BPOS. It is proportional to the gas density, velocity dispersion, and the correlation angle dispersion. So here is the correlation angle, and here the magnetic field on the right side. And so now if we can measure the dispersion, velocity dispersion, delta V, and we can measure the position angle dispersion, delta phi, and then we can get the magnetic field strength. Okay. So from observation, we can use a spectroscopy to obtain the velocity dispersion. So for example, we observe the absorption for some spectral line, and then we measure the line width, and then we get the dispersion, velocity dispersion. From the correlation map here, we can measure the angle dispersion, because the position angles in vicinity are not aligned, but they have some small fluctuation. And then we can measure the dispersion angle, and then we get the magnetic field strength. Okay. So recently people are improving the accuracy of the technique, but we still can only get the magnetic field strength projected in the planetary sky only. Now here, when we measure the magnetic field strength, we can estimate the magnetic energy. And then by comparing with the gravitational energy, we can see whether gravity can cause the collapse of clouds to form stars, or whether magnetic fields can resist the gravitational collapse. We just need to compare the gravitational energy and magnetic energy. So for example, here, the gravitational energy and magnetic energy is proportional to the mass divided by the flux, magnetic flux, to the order of 2. And then we can normalize the mass to flux ratio by some critical value. And then we get the dimensionless parameter lambda. So the dimensionless lambda here is proportional to magnetic field strength divided by the total gas Coulomb density and the gravitational constant. And here are some observation results. For example, so this axis showing the volume density of the gas, and here's the magnetic field strength along the left side. So these magnetic fields are obtained by the Zeeman effect. So you see that in 2012, at the time, observational data are still limited. So you see there are very few data points here. But the main conclusion from this study is in the dense region, with a density above 10 to the 4, gravity seems to dominate over magnetic field. So that means gravity can force the cloud collapse and form stars. So here, you see, most of the data points are below the critical line. And after about 10 years, there are a lot of observation results. And you see that here, there are more data points. And most of new data points here are actually obtained by the dust polarization using the DCF method. Because after 10 years, the advancement in Z-map technique is not so impressive. But dust polarization can allow us to measure many data points here. Yeah, so we now even can measure the magnetic field strength across a cloud. So all the results here are actually each data point here correspond to one measurement to one cloud only. But recently we can manage to measure the magnetic fields for each pixel across the cloud. So here, for example, from 30 Doradus, which is a massive star forming region. And there are many massive stars here, and these regions are affected by strong feedback. And using the DCF method, we can obtain the magnetic field strength. So you can see here, the color coding shows the magnetic field strength. And then when we compare the magnetic energy to the gravitational energy, we can see that in the region here, in most of the region, magnetic fields seem to dominate over gravity. So there are also new stars formed here. Now, how about magnetic fields near galactic center? You know that in our galactic center we have a supermassive black hole, sometimes it's A. And these supermassive black holes may be still accreting matter. And the magnetic fields will also may have some effect in evaporating the gas, feeding the black hole. So we can measure magnetic fields in order to see whether matter can be allowed to feed into black holes. So using the dust formation observed by Sophia, we can measure magnetic fields near black hole. So you can see that two different wavelengths, like 53 micron and 200 micron. And the magnetic fields seem to vary significantly from region to region. For example, in the mid region, the magnetic fields are very strong, but in the near black hole region here, the magnetic fields seem to be significantly lower. And by comparing the gravitational energy and magnetic energy, we show here the lambda diameter. So you see that in this region, lambda is smaller than 1. That means gravity is subdominant compared to magnetic energy. So star formation is quite slow in this region. It's also consistent with observations showing that star formation rate near the galactic center is rather low. And we don't know why. Maybe magnetic fields resist gravitational collapse. Reduce the star formation. Okay, so we were discussing about the effect of magnetic fields, and then we measure magnetic fields. But all magnetic fields we measure are only the component either along the left side or the component projected onto the plane of the sky. But intrinsically, magnetic fields are 3D, 3D-dimensional. So as you can see here, here is the model for 3D galactic magnetic fields, and here 3D model for magnetic fields surrounding the proto star. So we have to measure 3D magnetic fields in order to understand accurately the effect of magnetic fields. 3D magnetic fields are also important for other astrophysical problems. For example, for the transport and acceleration of cosmic rays. So cosmic rays coming from the distant galaxies, and then when they cross the galactic environment, they will be deflected or scattered by galactic magnetic fields. And 3D magnetic fields can allow us to model the scattering of cosmic rays. And 3D magnetic fields are important for star formation and planet formation, as you know. 3D magnetic fields are also critical for measuring the primordial gravitational waves using CMB mode signal. So we need to measure 3D. But so far, there's no any technique that can allow us to measure magnetic field. And we propose a new technique that can measure 3D magnetic fields using dust polarization. So basically, if we measure the dust polarization map, we get 2D magnetic field. And now, if we can measure the polarization degree, and then we can get one more component of magnetic field, and then we get 3D magnetic field. So first, we need to develop the model for the dust polarization first. And the model here is based on great alignment. For example, here's a 3D magnetic field, and here's a planetary sky, X and Y. And here's the light outside. And the dust grain is aligned with the magnetic field. And the magnetic field has two components, the planetary sky component and the light outside component. And the polarization function, will depend on the inclination angle, gamma. The gamma is the inclination angle between the local magnetic field and the light outside. So we can, I can walk you through the derivation of how polarization depends on the inclination angle. So, for example, here we measure the intensity of dust emission. It's given by the black body and optical depth. Because the optical depth along the X direction and along Y direction are different, because grains are elongated. If the grains are spherical, and then we have an optical depth along X and Y are the same, but here the grains are elongated, so they are not the same. And then to calculate the polarization fraction, we take the difference in the intensity along X and Y. And then the polarization fraction now, it becomes proportional to the difference in cross-section. Cross-section along Y and along X. Okay. And the cross-section along X and Y, the difference now is proportional to the inclination angle and the alignment degree. Alignment degree between the grain and the magnetic field. And the C4 here is the difference in the polarization cross-section along grain principal axis. So for example, if the inclination angle is 0, that means the magnetic field is along the light outside, and then the polarization degree is 0. But if the inclination angle is 90 degrees, the polarization fraction is maximum. And then if at the intermediate angle, the polarization fraction is smaller than maximum, so it's larger than 0. And then we now get the polarization degree as a function of the intrinsic polarization times the alignment and times the inclination angle. Yeah, so now if we can measure the polarization, we can infer the inclination angle. Okay, the polarization that we can observe here, and the intrinsic polarization depends on grain shape, and then the alignment degree, and some parameters which characterize the fluctuation of magnetic fields. And then based on the inclination angle and the planetary sky component, we can get the 3D magnetic field strength by combining the light outside component and the planetary sky component. So it is quite convenient to measure 3D magnetic fields. But we have to test with technique first. How we can test with technique? In order to test with technique, we first test with the synthetic data. Synthetic data, that means we generate data from simulation. And indeed, in order to perform a synthetic simulation, we need to know the alignment efficiency, we need to know the fluctuation of magnetic field, and the polarization angle, polarization fraction we can from observation. So we need to test. I think the most tricky problem is to calculate or to get the alignment degree, like how well grains are aligned with magnetic field. From observation, of course, we can get the polarization fraction, and then magnetic fluctuation. So we need to calculate first the alignment degree, and that is linked to the grid alignment physics. So we know how long we.
Yeah.
Fine. Okay. Yeah, so for grid alignment physics is quite complicated, but we can put it in one single slide. Basically, the dust grains, in order to be aligned with magnetic field, they must be magnetized first, and that means the dust grains must have a magnetic moment. And one of the mechanisms for magnetizing dust grains is through the magnet effect. So basically, that in the magnet effect, if the grain here containing many unpaired electrons. So you know that each unpaired electron has a one microscopic magnetic moment. But within the dust grains which are non-rotating, all electron spins are randomly random. So the net magnetic moment is zero. But when the dust grain is spinning, all electron spins are like along the rotation direction. So this is from the magnetic effect. And the magnetic effect is actually opposite to the Einstein-de-Haas effect. If people work on condensed matter physics, you know about the Einstein-de-Haas effect. So Einstein-de-Haas first demonstrated that there is an intrinsic link between electron spin and macroscopic rotation. So Baghdad just takes it in the opposite way. If we can spin the dust grain, and then we can align the electron spin. And then the dust grains, if it has a magnetic moment, it will precess around the ambient magnetic field. And then now we have the coupling between dust grain and magnetic field. And in order to have a very efficient alignment, you also need to have an internal alignment. So internal alignment is the alignment between grain axes. For example, here with angle momentum. And the internal dissipation of energy can help to reduce grain rotation energy and make the grains to be aligned along the minor axis. And there are two very popular mechanisms proposed by Edward Purcell in 1979. So the first is includes barrier mechanism and inelastic relaxation mechanism. So Purcell was the physicist working on condensed matter physics. And at the time, I think when he retired, he wanted to work on something else. And then he looked for the interesting problem in astrophysics, and then he started working on grain alignment. Yeah, so that is the, in terms of the time scale, you can see that the alignment time scale by Baghdad effect compared to the gas randomization time scale is very short. It's much shorter in the function of grain size and gas density. And N cluster here is the number of iron atoms per cluster. Yeah. So the magnetic relaxation is very fast in aligning dust grain. And for external alignment, the Langmuir reception time scale is even much faster. But the Langmuir reception has to couple the angle momentum to magnetic field only. In order to align, the angle momentum need to be along the magnetic field. And there are several mechanisms that can allow us to align the angle momentum with the magnetic field. So including here the magnetic relaxation and radial torques and mechanical torques. Because I don't have much time to discuss more about it, so I will jump into the results. Yeah, so when we have a theory, we now need to put in the simulation in order to generate synthetic data. And we developed the tool named the Polaris, like polarized radio simulator for this. And the code was first developed by Stephen Price in Viện Vật in 2016 as his PhD thesis. And currently, my student is improving the code by adding the latest development in dust physics, including the new alignment mechanism based on magnetic relaxation and radial torques on that. We also include other effects, including also the disruption. So the code is now very advanced. Yeah, so I show you here some very technical slides. about how the code design is. So basically, the code has several modules. First is about the module for astrophysical objects. The second module is for the radiative transfer. And the third module is about the dust physics. Okay? And this is the original model, but now we add more dust physics. For example, we include the internal alignment, and we also include the dust magnetic properties. So magnetic properties of dust are very important for polarization. And yeah, so this we even add more about the mechanical properties of dust. For example, how the dust grains are porous. So with this code and the most advanced dust physics, you can generate very accurate polarization data to be compared with the position. And here are some slides for our setup. So our simulation is a filamentary structure. And initially, the magnetic fields are perpendicular to the filamentary structure and for the dust grains. And the physical side of the filament here is about 50%. And we can run and calculate the grain alignment efficiency across the map to get the average alignment efficiency along the line of sight. So for different alignment model, so for example, for the ideal case, the alignment efficiency is quite large, about 1. So 4 grains are there. But for the grains that have a iron inclusion, which are super parametric material, so the alignment efficiency is larger. So the main conclusion here is if dust grains become more magnetic, or they have a higher magnetic susceptibility, and then the alignment efficiency is larger. And we also calculate the effect of magnetic turbulence, because in the model of polarization we have an alignment degree, equation angle, and the turbulence parameter. And here's a synthetic polarization map for different alignment model. And we compare the synthetic data with a simple model. And you see that it has a very well correlation between the model and synthetic data. So the model, simple model, works very well. And then with this model, we can infer 3D magnetic fields. So we did 3 maps: synthetic polarization, alignment, and turbulence. And then we get the elevation angle. Okay. So it's a map of elevation angles. It's quite not so easy to understand, so we plot it in the histogram. So we compare the elevation angles inferred from simulation with the real elevation angle. For example, here's the, we know from a simulation, we know the real elevation angle. Here, for example, the gamma B is the elevation angle. And here's our results. So the difference between the inferred elevation angle and the real angle is clear. So this is compared to previous studies which obtained the elevation angle by not considering grain alignment, shown by dashed line here. So our models reproduce much better the real 3D magnetic fields. So the next step is, okay, we need to test for more simulated data in order to analyze the real data. And when we are satisfied with our technique, we can use the real observation data and infer the 3D magnetic fields. So this is the first time we can obtain 3D magnetic fields using the combination between observation and dust physics. Here we show more about the comparison between magnetic field strength from the simulation and from the real data. You see the difference in the real data and inferred magnetic field is quite small, just less than 5%. And compared to other techniques here, of course, the difference is much larger. Okay, so we can apply the technique to the real 3D magnetic fields, and we already discussed several objects that have a well tested data, like the snake filaments that we we published one paper is now finished. And we have a data set for other filaments. So the next step we will apply the technique and then get 3D magnetic fields. Understanding the magnetic fields for astronomy. Okay, so let me summarize. So our cosmic ecosystem is very interesting. It contains a lot of things, including the life, planets, stars, black holes, and also the environments around it. But in the fundamental physics, it seems that only two fundamental forces, gravity and magnetic fields, regulate the evolution of cosmic ecosystem. And the current efforts in the field is to measure accurately magnetic fields, not only 2D but 3D. And if we can generate the 3D magnetic field maps of the whole cosmic ecosystem, and then it can help us to understand the evolution of cosmic ecosystem, but it also essential for advancing other fields of astrophysics and cosmology. And thank you very much for your attention.
Thank you very much, Thiêm. And now the floor is open for questions, comments. Yes, please.
We study evolved stars, how they die at the end of their life. And there are measurements of the magnetic field, and not many, but there are some. And people do measure fields, strong, Gauss scale at the photosphere. But it stops there somehow. I mean, all what we know about the way the star evaporates ignores that. And also grains are essential, but it's mostly grains, aluminum, or, I mean, it's collision of the stellar radiation. So it's a bit frustrating, if you want, because one thinks as a physicist that a magnetic field should play a role, but in fact, we don't know how to do it. Do you have any comments?
Yeah, I agree with your assessment. In fact, most of the measurements of magnetic fields in the star are taken by the maser-eyes. And the measurements are actually from very compact region. So what we would like to do is to have a map of multiple scales of magnetic fields using dust formation. So recently, from our modeling book, we show that the correlation is quite strong. So it could be observed. So I encourage observers to propose and measure the dust formation test. But about the effect of magnetic fields, there are actually some studies that show the correlation between magnetic field strength and the mass loss. So magnetic fields have some effects there, but we need more measurements to see to see the accurate magnetic field strength there. And with the limitation of Zeeman effect, it's very expensive in terms of Zeeman techniques. So dust correlation is quite cheap, but it has also some limitation because it's not so accurate as Zeeman. Yeah, but I think that the magnetic fields in Evo star won't be developing. So based on the recent research of the community, they explore different techniques.
I heard you mention the Einstein has the effect, but I wonder, is it include the spin orbit coupling or not? Because normally in condensed matter physics, if we consider magnetic field effect, we can also consider the spin orbit coupling.
Spin orbit coupling. So here the effect is about how to align electron spins. And so it's by rotating the dust spins, we can align the electron spins. So we do not consider the interaction between spin orbit, just spin orientation. But the effect of here is a nuclear relaxation. So magnetic relaxation is related to the electron spin, but the nuclear relaxation is related to the nuclear spin. So in that picture, we take into account the nuclear spin, interaction between the spin.
Okay, I have more general questions.
Yeah.
You have to actually apply the technique to reconstruct the 3D structure of the magnetic field to the synthetic data first.
Yeah.
So what's the purpose of that? Just to validate the model, to show that the model can reconstruct the 3D structure accurately? Or you need to apply it to get some...
First, we test the model, because from observation, the correlation fraction depends on so many parameters. Thus, physics, magnetic field fluctuation. And it's quite difficult to model the dust correlation. And now we develop first the model of dust correlation. So in this model of dust correlation, it has several parameters, like the trend shape, the alignment degree, and the turbulence parameter. And with the from the synthetic simulation, we can control these three parameters. And then we can test, okay, with this simplified model, we can accurately reproduce the synthetic data. And then next step is to apply the model to the real data. Because if the model works with the synthetic data, it can work with the real data. And then we can infer the integration data.
I see. So the first to refine the model for...
Yeah,
to
best match the real data.
Yeah, I recommend is that nature is always more intelligent
than
us. So this is very simple.
Yeah.
In reality, no guarantee that reality is like this.
Yeah, so that we need to go step by step if we really do want to understand the real nature.
Okay. Yeah. The other question? Comment? One small question.
Yeah.
Look at this formula, for example. So there's a physical property, right, related to magnetic field, also to turbulence.
Yes.
Now, here they talk only about the dust, right?
Yes.
The turbulence associated with dust. But there's another component, that's a gas. So my question is that can you use observation from, for example, H1 or CO, actually estimate the property of turbulence kind of independently from...
Oh, okay, that is a very good point. Actually, here the F turbulence is to describe the magnetic field fluctuation. So basically, it is not needed to be related to anything. So in fact, dust and gas, we always assume that they are coupled. And when they are coupled, they move together. So the fluctuation of the gas is also the fluctuation of the dust. And so usually, people measure the angle dispersion, the velocity dispersion, which is another key parameter for measuring magnetic fields, using the molecular lines, or CO lines, or ammonia lines. So in terms of measuring the F turbulence here, because the fluctuation here is about the fluctuation of magnetic fields, not the gas motion. So we can measure the F turbulence based on the fluctuation of position angles. So the position angles could be from the dust position or from the other correlation, from the Zeeman techniques. So for any tracers, that tells us about the fluctuation of magnetic fields. But of course we use the dust correlation vectors to calculate F turbulence because it's convenient and it's available from our measurement.
Okay. The other thing is here I'm very curious, right? The model for dust alignment seems to be very simple because dust grain seems to be kind of spherical, right? But in reality, actually, dust grain are highly inhomogeneous, right? It's a kind of spectrum morphology, right? There's no guarantee that what you draw here is reality.
Right. We don't know what the reality is. So in terms of model development, we are based on the physics. Of course, there are different approach. So people who try to fit the data, they can come up with a very complicated model that can accommodate the porosity, the structure, the shape. And one of the examples of that is QUÄC. So Bruce Lane, after more than 40 years, he has developed...
He's still active, right?
Yeah, he's still active. He has been developing the best model that is most consistent with the data. And of course, for 30 years, he proposed that the dust consists of silicate and carbon. And silicate and carbon are separate. And his model can excellently reproduce data. But after 40 years now, he wake up. He changed his mind. Because he proposed now that if silicate and carbon is mixed together with some porosity, some iron, the model even reproduce better the data. So each approach has a limitation. And our approach is different. We are based on fundamental physics. So we started from the actually condensed matter physics, solid physics, with the magnetism and rotational dynamics. And then our model has a quite flexibility because it can apply to the whole cosmic ecosystem. This is very different to the model by Bruce and Drain, that it is mostly applicable for the diffuse medium. Because the model is designed to fit the data from the diffuse medium. But our model, we can apply from the diffuse medium to dense cloud to the disk. So in the latest work that one of our student Thời, he has been looking on into the models of position for the disk. And it can work. So that is, when we are guided by the tested physics, I am glad in that approach. Because the model, empirical model can fit the data very well.
Did anyone try actually to test this kind of dust alignment model in the lab?
In the lab?
Because here it's remote sensing, right? You cannot actually touch the object, touch the dust.
So in the lab,
so in the lab, is there any way, or any attempt to actually test this?
So the first step in the lab is they tested the rotation of dust grains by radiation by NASA in 2004. So they showed a beam of laser to the dust grain and then they measured the rotation rate. And then they found that the rotation rate is actually as predicted by the radiating clock theory. And, of course, we also need to test the orientation of dust grain with magnetic field, but in terms of time scale, it's quite difficult to do.
Okay. Okay, any other question? Okay, so if not, then let's thank our speaker again for